very interesting that we looked into the motion of a sphere in an unbounded flow with the help of a consideration in the previous lecture, where we started first with a description in the Cartesian system and then we graduated into the polar system. So, this is where we were left in the end of the previous lecture, that you have the velocity components Vr and V theta expressed in terms of u infinity at far away from the sphere. So, now how do you get the Stokes stream function far away from the sphere? To do that, we will write the expression for Vr and V theta in terms of psi. So, let me write that. So, Vr is equal to 1 by r square sin theta and V theta, I am just writing separately, minus 1 by r sin theta okay. So, where from these expressions come? Nothing but a parametric form that satisfies the incompressibility condition in the polar coordinate system, nothing more than that. So, this is true even if r is not tending to infinity, but at r tends to infinity you have this expression. So, if you equate these two, so this will be u infinity cos theta. So, what will be psi? This will be integral of u infinity r square sin theta cos theta d theta. So, that will be sin square theta by 2, right, sin theta cos theta d theta, because if you take sin theta equal to z, cos theta d theta is dz. So, z dz will be z square by 2. So, u infinity r square by 2 sin square theta plus this is partial integration with respect to theta. So, the constant of integration is a function of r, which is like a constant. Here the variable when you are integrating, this is called as partial integration. So, when you are integrating, the variable of integration is theta, any other variable is treated like a constant. So, here again this is this one minus u infinity sin theta is this one. So, psi will be, now here the variable is r. So, r dr is r square by 2. So, u infinity r square by 2 sin square theta plus a function of theta. It is not surprising that these two are the same, they are supposed to be the same, because no matter how do you derive it from Vr or V theta, psi expression should be consistent. So, from these two, by comparing these two, you can set this function of r, because it should be a same expression, equal to the function of theta is equal to a constant, otherwise they will not be the same equation. What is the value of the constant? The value of the constant can be chosen arbitrarily. So, for all practical purposes you can write the psi at the far stream as u infinity r square by 2 sin square theta plus a constant which may be set to 0 as a reference. It can be any constant, not necessarily 0, but I mean for all algebraic convenience you can set it to 0. So now given that this information that you have at r tends to infinity, if r is not tending to infinity, typically if r small r is close to the surface of the sphere, what form of psi you expect? See, as you go from the surface of the sphere to far away from the sphere, which dependence changes, r dependence or theta dependence? If you go from surface of the sphere to far away from the sphere, what dependence changes, r dependence or theta dependence? R dependence, because it is the radial coordinate that demarcates whether it is in vicinity of the sphere or far away from the sphere. The theta dependence can be very similar. So we can assume, again I am deleting the unnecessary part from the board. So we can write that for finite r the theta dependence is sin square theta and function of r is equal to u infinity r square by 2 if r tends to infinity, but for finite r it will be something else. See, this is a separation of variables essentially, a function of r into a function of theta. If you look into mathematics books, this is where from which they will start the solution, but there should be a physical basis of why you are choosing this form, and that is very very important for conceptual understanding. So I hope I have clarified why we are choosing this form. Now let us calculate these E square operators. So what is I am just using this. So this will be the derivative with respect to theta will be 2 sin theta cos theta, right. So then this one of the sin theta gets cancelled, then the partial derivative with respect to theta cos theta will be minus sin theta. So this will become minus sin squared theta, therefore it will be f double dash minus 2f by r square sin squared theta, okay. So this is a function of r, let us say this is g of r, right, because f is a function of r, its all derivatives etc. these are function of r. So E square psi is equal to g r sin square theta. So what will be E square of E square psi? This is like an aptitude test. So what will be this? G double dash minus 2g by r square sin square theta, right. just replace f with g. So, this equation essentially boils down to g double dash minus 2g by r square equal to 0, right. So, this equation has a solution where g is of the form r to the power n. Okay. So, let in fact f is r to the power n because we start with f and then we move to g. So, both a and g are f and g are of the form of r to the power some coefficient. So, let f is equal to a r to the power n. So, f dash is a n r to the power n minus 1, f double dash is a n into n minus 1 r to the power n minus 2. Two f by r square is 2a r to the power n minus 2. So, f double dash minus 2f by r square, we will work it out here. This is a n into n minus 1 minus 2 into r to the power n minus 2. So, let us call this as b. So, this is g, right. So, now you tell what is g double dash minus 2g by r square. This will be b. Similar formula, replace n with again like aptitude test, replace n with n minus 2, right. So, b into n minus 2 into n minus 3 minus 2 into r to the power n minus 4, right. So, what boils down to is, so now this b is what, a n into n minus 1 minus 2. So, g double dash minus 2g by r square equal to 0, what it means is that n into n minus 1 minus 2 n minus 2 into n minus 3 minus 2, this is equal to 0. So, this is a quadratic in n, this is a quadratic in n, that means there will be 4 roots, right. So, let us find out that. So, n square minus n minus 2, this is n square minus 3n minus 2n. So, minus 5n plus 6 minus 2 plus 4. See, this is why in school we study factorization. In class, I can remember when I first studied factorization in class 7 or 8, I cannot remember correctly, I never realized that for such a glorified thing like Stokes flow past a sphere, that factorization will be required, but I mean that is the reality, now we have to do that. So then n square minus 2n plus n minus 2, this is n square minus 4n minus n plus 4 equal to 0. So this is n into n minus 2 plus 1 into n minus 2, this is n into n minus 4 minus 1 into n minus 4, right. So you have n plus 1 into n minus 2 into n minus 1 into n minus 4 is equal to 0, right. So n is equal to minus 1, 1, 2, 4, okay. So what is the general form of f? F is C r to the power n, but because of linearity, for the solutions for all values of n, they should be linearly superposed to get the general solution. So it is C1 r plus C2 r square plus C3 r to the power 4 plus C4 by r, right. Okay. So how do you obtain these values of C1, C2, C3, C4 etc.? You have to use the appropriate boundary conditions. So let us draw that sphere. Sphere is here, this is capital R, radius of the sphere. So what are the boundary conditions physically? See, always understand this, before writing any boundary condition mathematically, try to have a physical picture of what is the boundary condition. This is very, very important, then you will never make a mistake of writing the boundary condition. So what is the boundary condition at the surface of the sphere? There are two important considerations. One is a pure kinematic consideration, that fluid cannot penetrate through the sphere. So that is called as no penetration boundary condition. So at smaller equal to capital R, you have Vr equal to 0. Let us write first in terms of velocity and then we will translate that to stream function. This is no slip, this is no penetration, this is no slip, and at r tends to infinity, the velocity should be the stream function should be the stream function at infinity that we have found out earlier. So what is that? U infinity r square by 2 sin square theta, right. So this is called as, in fluid mechanics there is a language, like in everything there is a grammar. This language is called as first stream boundary condition. Like sometimes people will not write it explicitly, but first stream boundary conditions means it should match with what happens at the first stream. Whatever solution that you are coming up with, it should match what is at the first stream. So now what is only left is these you have to convert in terms of stream function. So, no penetration means what? No penetration means flow is always tangent to this if at all there is a flow, there is no normal to this flow normal to this boundary. That means this is like a streamline. The definition of a streamline is that you have flow always tangent to the streamline and there is no flow normal to the streamline. Okay. So, if you are having no flow normal to this, that means this acts as a streamline. A streamline by definition is having a constant value of stream function. So, psi is equal to a constant over the surface of the sphere. That constant you can take arbitrarily, so let us take as 0. So, this no penetration boundary condition becomes equivalent to f equal to 0, and v theta, remember in the Cartesian system u is defined in terms of stream function as the derivative of psi with respect to y. Here in the r theta system v theta is defined as the derivative of psi with respect to r, right. So, derivative of psi with respect to r is nothing but the implication, having the implication of f dash. Okay. So, the boundary conditions, and so this is f at r tends to infinity. So, we have the 3 boundary conditions. The interesting part of this mathematical problem is that there are 4 constants, but you have 3 boundary conditions, and you will see that how using the physical nature of the problem you can eliminate one of those constants. So, let us put these constraints at small r equal to capital R, f is equal to 0, that means C1 r plus C2 r square plus C3 r to the power 4 plus C4 by r equal to 0. At small r equal to capital R you have f dash equal to 0, that means C1 plus 2 C2 r plus 4 C3 r cube minus C4 by r square is equal to 0, and at r tends to infinity f is equal to u infinity r square by 2. So, from here what can you conclude? From this what can you conclude about the constants? Yes. So, the first thing that you can conclude is C2 is u infinity by 2, because r square dependence should match with r square dependence. So, C2 is equal to u infinity by 2. Not only that, C3 is equal to 0, because the maximum dependence on r as you come up at r tends to infinity cannot go to a power beyond that, beyond 2. So, that means you have C3 is equal to 0. So, once you have C3 is equal to 0, these terms are gone. So, you can calculate C1 and C4. So, you can for example divide this by r, the first equation divide by r. So, you will have C1 plus C2 r plus C4 by r square is equal to 0. So, now you can find out C1 and C4. So, for example, if to find out C1 you can add the two. So, if you add, you have 2 C1 plus 3 C2R. So, 3 u infinity by 2 r is equal to 0. So, C1 is minus 3 u infinity r by 4, right. And then you can substitute in one of the equations to get what is C4. So, for example, C4 by r square is equal to minus C1 minus C2R. So, 3 u infinity r by 2 minus C4R, sorry, minus C2R. So, minus u infinity r by 2. Is there any algebraic mistake? You let me know, right. If there is any algebraic mistake, you please let me know. So, this becomes u infinity r. Okay. So, the procedure is pretty straightforward. The algebraic details you can of course recheck it, and if everything is done properly, let me give you the final expression. So, there may be some mistake. This is minus C1, this one and minus C2R. So, C1 yes, C4 by r square minus C1 minus C2R, whatever. So, the net expression so there hopefully that I do not I will check it once, but let me write the final expression. So, the final expression is f is equal to, or the psi equal to u infinity r square by 2 sin square theta plus one minus 3 by 2 r by r just check these ones, the values of C1 C2. One of the things I am finding 3 by 4, the other there is a 1 by 4 somewhere coming. This is 3 by 4, huh? Yes. So, minus so this is u infinity r by 4, right. So, this was 4, sorry, yes, not 2. So, now it matches with the final answer that I have with me. So, in principle this is all, because once you know this is the solution of the stream function for the problem. From the stream function you calculate velocity, because you have the expressions for velocity as a function of the stream function. But what is your end objective? The end objective will be to calculate the drag force on the sphere. So, in our next lecture we will see that how, starting from an expression for the stream function, we can calculate what is the drag force on the sphere. But remember, this is the most fundamental thing. This gives the velocity field. In fluid mechanics, if you have the velocity field, you can get all other derived parameters from the velocity field itself, and that we will take up in the next lecture. Thank you.